The member has a rectangular cross-section that's designed to resist a moment of 40 Newton meters. In order to increase its rigidity and strength, it's proposed that we're going to add these two little ribs to the bottom. And so what we want to do is we want to figure out what the maximum normal stress in both these cases are and figure out if the ribs really are helping us at all. So let's do the first, we got both cross sections here. Let's start with the easy one. And the reason I say this is the easy one because we don't really have to calculate out a centroid because it's rectangular. We don't have to worry about the parallel axis theorem. So let's just dive right into it. So we know that the maximum stress is going to be what? It's going to be MC over I, our moment times the largest distance from the centroidal axis or the neutral axis to the outside surface. And I say the largest distance because we just want to know the maximum. So we've already been given our moment for both of these problems, 40 Newton meters. So we don't have to calculate anything out there. So let's look at our moment of inertia. That's pretty easy. Moment of inertia is just base height cubed over 12. And so in this case, our base is 60 millimeters or 0.06 meters. Our height then is 0.03 meters. And we're going to cube that. We'll divide that whole thing by 12. And once we bash that into our calculator, we get 0.135, 10 to the negative 6 meters to the fourth. Okay, and our distance, our neutral axis is a rectangle. So it's going to be right along the middle. So our C value is going to be 15 millimeters. And it doesn't matter bottom or top since they're both the same. So the compressive and the tensile strengths in this one are going to be the exact same. So we'll just plug everything in. 40 Newton meters times C, 0.15 meter, divided by 0.135 times 10 to the negative 6 meters to the fourth. Check out our units, meter squared up there. That's going to leave us Newton meter squared, which is a Pascal. And so we'll have 4.44 megapascal, or 4.4 times 10 to the 6 Pascal. And so this will be either tensile or compressive because it's the exact same whether we go up or down. And if you look at the way that we're bending, so we're bending upwards, so we're making that little smile. So the top is going to be compressive, the bottom is going to be tensile. Easy, easy, easy. Now let's look at this guy. This guy gets a little bit more complex. We're still solving the same equation. Stress max is, MC over I. M is going to be the exact same. M doesn't change. What's going to change, though, is C and I. So we're going to have to calculate out the centroid, and then we'll have to do the parallel axis theorem. So for our centroid, y bar is going to be equal to the sum of the individual y bars times the areas times the area, the overall area. And so now what we have is, I'm going to break this up into two pieces. So we're going to have the overall big one, the guy that we just did, and then we're going to do those two little individual ribs. So let's start with the first one. The centroid, and we're going to measure everything from, let's see, what's going to be the easiest way to do this? We're going to make the bottom of our ribs our y equals 0, and then we'll work our way up from that. Do I want to do that? No, that's probably not a good way to do it, actually. So we're going to go right from the top here. That's going to be y equals 0, and we're just going to work everything down from there. So the first one, the y bar of that first area is going to be 0.15 meters, and then the area will be 0.03 meters times 0.06 meters. And so that takes care of that larger area first. And now we're going to have that smaller area, these two little ribs here. And so first we'll do the area, 0.005 meter times 0.01 meter tall. And, that's not going to fit on the denominator. So we're going to bring the rest of the numerator over here, just because we're running out of room. Actually, let me make that a little bit tighter. And so now what we have to do is multiply that by its y bar distance of just that area. It's a rectangle, so it's going to be in the center. So it's going to be 2.5 millimeters below the bottom. So that's going to be 30 plus 2.5 millimeters. So what we have is 0.0325 meters. And that's the distance from the top to the centroid there. And then we have two of them, so we'll multiply that by 2. We'll get both of those in there. So we're going to have all that over the sum of the area. So the area is going to be 0.03 meters times 0.06 meters. That's the area of that first larger section. And then we're going to add to that 0.005 meter times 0.01 meter. That's the area of one of the ribs. We're going to multiply that by 2 to get both of the ribs. And so our y bar for this guy is going to end up being 0.01592 meter. This is a little bit south of where the other one was. Now, because of that, we have a different C value. Because remember, C is going to be the largest value, or sorry, it's going to be the distance from the neutral axis to the outside surface. Now, in this case, we want the largest of the two. So, to get to the top, which would be the maximum compressive stress, it's going to be this 15.92 millimeters. So this entire thing, though, is going to be 35 millimeters tall. We'll subtract from that 15.92 millimeters. And then what that's going to tell us is to get to the bottom, where our maximum tensile stress is going to be, it's going to be 19.08 millimeters. That's a larger number than 15.92. Therefore, our tensile stress will be the highest stress in this bar. So C for us is going to be 0.01908 meter. And so it'll be the maximum tensile stress in this situation. Okay, and now we got to do the parallel axis theorem because we need that moment of inertia. And so I is going to be equal to the sum of the moment of inertia about their own centroids plus AD squared, where A is the area of the particular piece and D is the distance between the centroid of the little piece and the overall centroid of the composite shape, which is this guy right here. So let's start. Once again, we'll start with the first one. And so the first one, we've already, if we go back here, if we go back to the last problem, I already know what its moment of inertia about its own centroid is. 0.35 times 10 to the negative 6 meters to the fourth. Now I have to add to that the area times the distance. And so our area is 0.3 meter, 0.6 meter. And now I need to know how the distance is affecting things. Well, how do we calculate that out? Well, the centroid of the composite shape, 0.1592 meter, minus the centroid of that piece, which is 0.45 meter, and then we want to square that difference. So, just the closer that its local centroid is to the overall composite centroid, the less extra effect that it has on things. Okay, and so now we go to the ribs, and so we're going to add that to there. And so we're going to do, 1/12 base height cubed of the rib. So the height is 0.01 meter. The height is 0.005 meter cubed. We will add to that the area, 0.01 meter times 0.005 meter. And now we have to do the distance to get that. And so the distance is going to be 30 plus 2.5. So that was going to be that 0.0325 meter. And I'm going to subtract from that the location of the centroid. Probably looking at that and going, wait a second. And the one above, you did the location of the composite centroid minus the local centroid, and there you did it the other way. Which one is right? It doesn't matter. Since we are squaring it, we're just trying to figure out the distance between the two. You're going to get the exact same answer no matter what you do. But we do have two of those, so what I'm going to do is I'm just going to take this guy, multiply that part by 2, because there is going to be no change between the two of them, and that's going to give me a moment of inertia for this shape, this composite shape of 0.1642 times 10 to the negative 6 meters to the 4th. And we just throw it into our equation. Maximum stress is going to be 40 Newton meter times our C value, and we're taking the bigger one because I want to know the maximum stress. Now I could go back and figure out the maximum compressive stress, but I just want to know the overall maximum stress. I'm going to divide that by 1642 e to the negative 6 meters to the 4th. I'm going to take a look at my units and go, yep, those are right. Meters, meters, meters squared. That's going to leave me with pascals. And so when I plug that into my calculator, 4.65 megapascal. Now, if you look at that, it's like adding the ribs actually makes the stress worse, because without the ribs, we are looking at, I wanted to go back, but it's not letting me now. Without the stress, without the ribs, the maximum stress is 4.44 megapascals. With the ribs, it's 4.65 megapascals. Because we've added that material, we're bending it more. There's a larger distance going to the axis. It messes things up. But anyway, that's how we calculate it out.